Okay, hi everyone, I'm Zhefu Yu, a graduate student in the Ohio State University. Here I'm going to talk about the black hole mass measurements from the OzDES Reverberation mapping project. The supermassive black holes commonly exist as the centers of massive galaxies, and it is an interesting topic of how these supermassive black holes evolve over cosmic time. And in order to study the evolution of supermassive black holes, a critical parameter is the mass of the black hole. Beyond the local universe, the most accurate method to measure the black hole mass in AGNs is the reverberation mapping technique. And this figure here shows an example of how it works. The typical spectra of type 1 AGNs contains a parallel continuum from the accretion disk around the central supermassive black hole. The continuum ionizes the gas clouds in the broad line region, which produces broad recombination lines. Both the AGN continuum and broad lines are variable with time, and there will be a time delay between the variation of the AGN continuum and broad lines. And this time delay corresponds to a large travel time from the accretion disk to the broadline region, and therefore it indicates the typical size of the AGN broadline region. According to the virial theorem, we can use the broadline region size and the width of the broadlines to calculate the black hole mass, as shown in this equation here. This slide shows an example of how we measure the time lag between the continuum and broad lines. First, we need to monitor the targets for years to derive the light curve of the continuum and broad lines, as the example shown in the left figure as the black data points. We then derive the probability distribution of the time lag from the light curve, as the example shown in the right figure. Here it shows a lag signal around a year. And if we look at the light curves, we can recognize this 1 year time delay between the continuum and line light curve. To make this more clear, the red data points in the lower panel shows the continuum light curve that are shifted by this 1 year time delay. And here the shifted continuum can well match the line light curve, which verifies the reliability of this lag signal. And measuring the time lag is observationally expensive, since we need to monitor the targets for years to derive the light curves. And an important finding in previous reverberation mapping studies is a strong correlation between the broadline region radius and the AGN continuum luminosity, as the example shown in this figure. Using this RL relation, we can estimate the broadline region radius and calculate the black hole mass using just a single epoch spectra, which is less accurate but much more efficient, and allows us to estimate the black hole mass for a large sample of AGNs. However, most of the lag measurements from early reverberation mapping studies were limited to low redshift, low luminosity AGNs, and in those studies, the RL relation was mainly based on the time lag of the H-beta line, while the RL relation for the magnesium 2 and carbon 4 line were poorly constrained. It would be important to measure the magnesium 2 and carbon 4 lags for more quasars to better constrain their RL relation, since those RL relations are the key to the black hole mass estimates at high redshifts. This motivates some industrial-scale reverberation mapping campaigns with large sample and long monitoring baseline. And there were two large campaigns that started around the similar times. One is the Sloan Reverberation Mapping Project based on the Sloan survey, and the other is the OzDES Reverberation Mapping Project based on the dark energy survey. So the DS is a 6-year photometric survey that covers about 5,000 square degrees in the sky, and the OzDES survey is the spectroscopic follow-up survey in the DS supernova fields. The OzDES Reverberation Mapping Project monitors 771 quasars for the whole duration of DES. We have about weekly photometry from DES and have about monthly spectroscopy from the OzDES survey. We have published a set of papers on our data analysis and initial lag measurements, and there would be more results to come out in the near future. The OzDES spectra were taken from the 2DF multi-fiber spectral graph. It is non-trivial to calibrate the fiber spectra, while the calibration is also critical for our light curves and lag measurements. In the Holman 2019 paper, we developed a pipeline to calibrate our spectra using the DES photometric light curves, which naturally accounts for the quasar variability over time. This figure shows an example of the calibration process. First, we calculate the scaling factors from the integrated instrumental flux to the DS photometry at GRI bands. We then interpolate these scaling factors by a second-order polynomial. Then we multiply the scaling function to the uncalibrated spectra to derive the calibrated quasar spectra. It is also non-trivial to estimate the uncertainties from the calibration process. And in my most recent paper, we developed a Monte Carlo framework to estimate the calibration uncertainties using the f-stars monitored in the same fields. And as an example, the upper panel in the left figure shows the beam spectra in multiple epochs of a single f-star, while the lower panel shows the residual variation of this spectra. If we think that the f-stars do not vary over time, then this residual variation can be seen as an estimate of the calibration uncertainty. We then define a warping function as the single epoch f-star spectra divided by the mean spectra, as examples shown in the right figure. And each of these warping functions can be seen as a realization of the variation caused by the calibration uncertainties. We can use these warping functions to propagate the calibration errors into the error budget of the broadline flux using a Monte Carlo framework. And this method naturally accounts for the error correlation over different wavelengths, which would be important if we fit a wide wavelength range. Another challenge in doing reverberation mapping for the magnesium 2 line is the strong iron emission around this wavelength range. And in this project, we model the AGN continuum using a power law and model the iron emission using the iron templates from literature convolved with the smoothing kernel to account for the velocity fields in the broadline region. We then perform a MCMC fitting to derive the model parameters. The blue solid line in this figure shows the best fit continuum, while the red line shows the best fit continuum plus iron emission. And here we can see that our best fit model can well match the observed spectra. And in my most recent paper, we are excited to publish our initial lag measurements for the magnesium 2 line. In this paper, we measure the magnesium 2 lags for 9 quasars, and here we show them in the RL relation plot. namely the correlation between the broadline region radius and the AGN continuum luminosity. Here our sample fills in a gap in the luminosity range where there were few existing lag measurements, and most of our lags are consistent with both the H-beta and magnesium II RR relation from literature. These initial measurements are based on only part of the OzDES quasar sample with only the first 5 years of data. And now I have finished the analysis of the full OzDES sample, and it is exciting that we obtain a large sample of new magnesium II lag measurements. In this figure, we show the preliminary lag measurements for 27 quasars, and this sample is a significant addition to the RR relation of the magnesium II line. With this sample, we expect to derive the best constraint RR relation for the magnesium II line to date. And we have also published our initial carbon-4 lag measurements in the Holman 2019 paper using the first 4 years of data. These two sources are among the highest redshift quasars that have the carbon-4 lag measurements. Again, there would be more carbon-4 results to come out in the near future. And in addition to the reverberation mapping of the broad emission lines, we can also use continuum reverberation mapping to measure the size of the AGN accretion disks. The basic idea here is that the short wavelength in the AGN continuum mainly comes from the inner region of the accretion disk, while the longer wavelength mainly comes from the outer region of the accretion disk. In this case, the time lag between the variation of different continuum bands corresponds to the light travel time from the inner to the outer disk, and therefore indicates the disk size. In one of my 2020 papers, we performed continuum reverberation mapping using the data from the DEF standard star fields. The left figure shows the distribution of the observational cadence in the DS fields, and the standard star fields have about daily observation cadence, which is quite high compared to previous studies using continuum reverberation mapping. And in this paper, we measure the disk sizes of 22 new quasars, and here we show them in the accretion disk size versus black hole mass plot. The 3 lines here show the prediction of the standard thin disk model with different Eddington ratios, and here our results are consistent with the prediction of the standard thin disk model, which is in contrast to some previous studies that find larger disk sizes than the model predictions in some local AGNs. And one lesson we learned from our experience with DS is that the observational cadence is critical for the continuum lag measurements. And in order to give some indications to future surveys, we performed some simulations in the LSST deep drilling fields. The left figure shows an example of our simulated light curves. The upper panel of the right figure shows the fraction of continuum lags that we can successfully recover from the simulated light curves as a function of the input time lag to the simulations, while the lower panel shows the distribution of the predicted continuum lag for Sloan quasars. And there are many quasars that would have small continuum lags, and for those sources, if we change a 3-day cadence to a 2-day or 1-day cadence, then we can significantly increase the yield of the continuum lag measurements. And we have also performed some simulations led by Andrew Penton to assess the reliability of the broad line lag measurements. The upper row of the left figure shows an example of our observed light curve, while the lower row shows an example of the simulated light curve. And here we can see that the simulated light curves show similar variability as the observed light curves. The right figure shows the distribution of the difference between the measured lag from the simulated light curves and the input time lag to the simulations. Here we can see a clear distribution around 0, indicating that our lag measurements are generally not biased. Based on this simulation, we define a set of quality cuts of the time lag, and using this simulation, we can also estimate the false positive rate of individual time lag measurements. And we have also performed some simulations led by Uman Malik for the survey design of future reverberation mapping campaigns. This figure shows the fraction of high-quality lag measurements in the space of magnitude and redshift. The deep colors means that there are a high fraction of good lag measurements around this apparent magnitude and redshift, while the light colors means that the fraction of good lag measurements is low around this area. And the lines with different colors mark the expected lag values. So the orange dashed line marks the half-year lag, while the yellow solid line marks the 1-year lag. The left column shows the results from a 5-year survey, while the right column shows the results from a 10-year survey. From top to bottom, we show the results where the length of the observational season is 5, 7, and 9 months. And for the results from an observational season of 5 months, we can notice the stripe features in the simulation results. That is, for a 1-year time lag, the fraction of good lag measurements is high, while the fraction of good lag measurements is low for a half-year lag. This is because that for the half-year lag, the lag measurements is significantly affected by the aliasing effect due to the half-year seasonal gap. And in order to overcome this seasonal effect, we can use longer lengths of the observational season. As we go from top to bottom with longer and longer seasons, this stripe features becomes less clear. This indicates that for future reverberation mapping campaigns, we want the seasonal length to be as long as possible to overcome the aliasing effect. And there would be more OzDES results to come out in the near future. In addition to the new lag measurements, we also plan to perform joint analysis of multiple broad lines to further study the broad line region structure. We also plan to calculate the single-epoch black hole mass for large samples of AGNs using our RR relations, and study the demographics of supermassive black holes. In summary, we monitored about 800 quasars for 6 years in the OzDES Reverberation Mapping project. Our results cover the broad line region reverberation mapping, the continuum reverberation mapping, and also some relevant simulations. We have published our initial results, and there would be more results to come out in the near future. And here I also show the papers that are relevant to these topics, and you can find more details on them if you are interested. Thanks for your listening.